Greetings, A-level chemists. Okay, here we've got a shapes of molecules question linked in to an intermolecular forces bonding type question as well, okay? So, question is, the melting point of xenon tetrafluoride is higher than phosphorus trifluoride. Explain why the melting point of these two compounds is different. State the shape of each molecule, why it has that shape, and how the shape affects its melting point. Okay, so how the shape affects the intermolecular forces effectively. All right, let's start with the shapes then. So, for XeF4, I'll do it from first principles, okay? Xe, so xenon has 8 valence electrons. Each fluorine contributes 1, so 4 are going to contribute 4 to the valence shell of xenon. So in total, that's 12 electrons. So to work out the number of electron pairs, divide by 2. So you've got 6 electron pairs. Thing is, we've only got 4 things bonded to it. So we're going to have 4 bonding pairs and 2 lone pairs, okay? So let's draw that out for xenon. Xenon in the center. And if you've got 4 bonding pairs and 2 lone pairs, the shape is going to be square planar, okay? And that bond angle there is going to be 90 degrees. Okay, you're also going to have a lone pair here and a lone pair there. It's not asked for the bond angle, so I'm just going to take those out for clarity. And this is square planar. So I'm just going to write down 4 bonding pairs and 2 lone pairs. Okay, this is symmetrical, so there is no dipole moment net. So it's a non-polar molecule. Okay, you've got dipole moments on the XeF bonds, but they all cancel out, okay? So there's no net dipole moment, it's a non-polar molecule. And what does that mean? It means you're not going to have, so no permanent dipole forces between molecules. Okay, so let's compare that to PF3. So we're comparing that to PF3. Just going to quickly go through the process. P's got 5 valence electrons. 3 times fluorine contributes 3. So you've got 8 electrons in total around phosphorus's valence shell. So you're going to have 4 electron pairs. You're going to have 3 bonding pairs and 1 lone pair. We'll just reiterate that in just a second, okay? So, if you've got 3 bonding pairs and 1 lone pair, the shape is going to be pyramidal or pyramidal. And you've got a lone pair on the central phosphorus, okay? Now, shape is going to be pyramidal. Let's just say we've got 3 bonding pairs. 3 bonding pairs and 1 lone pair. Now here, the dipole moments do not cancel out, okay, due to the shape. And that means we have a net dipole moment in this direction. So we've got a net dipole moment. So we have a polar molecule. So we have the permanent dipole forces of attraction between PF3 molecules. Now that actually doesn't answer the question as to why xenon tetrafluoride has a higher melting point than phosphorus trifluoride, so let's actually get to it. Now there's an additional intermolecular force that I haven't accounted for which occurs in both of these. In fact, it occurs with anything with electrons. So we've got van der Waals forces too, or London forces. Van der Waals or London forces as the main intermolecular force. Here we've got permanent dipole force of attraction between molecules and van der Waals forces. Okay, what we're really saying here is that the van der Waals or the London forces in xenon tetrafluoride must be stronger than the permanent dipole forces and the van der Waals forces in PF3 because the van der Waals forces scale with the numbers of electrons. So XCF4 has more electrons in total than PF3. So the London forces in XCF4 are stronger than the permanent dipole forces and the London forces in PF3, and those London forces in xenon tetrafluoride are going to require more energy to break. And there you go for your 6 marks. See you later.